Hi everyone. My name is Paul Boniol, and I will present our paper, co-authored by Michele Lenardi, Federico Roncallo, and Themis Palpanas. Our work is on unsupervised subsequence anomaly detection in large data series. We will first introduce the task and the problem definitions used by the state-of-the-art method for subsequence anomaly detection. We will then point out the shortcomings of these definitions, followed by the description of our approach, named norm. We will conclude with an experimental analysis comparing our methods to the current state of the art. Let's first introduce some basic concepts. We name a data series an ordered sequence of real-valued numbers. If the dimension that imposes the ordering of the sequence is time, then we name it a time series. A subsequence of a data series T is a small set of contiguous values of the series T. We define a subsequence using index I, indicating when the subsequence starts, and a length L. The subsequence ends at index I plus L. In this work, we are interested in identifying anomalous subsequences. Note that an anomalous subsequence is not a single value, but rather a sequence of values that can be abnormal, or unusual. This distinction is crucial for the following reason. Even if all individual values in a subsequence look normal when examined independently from one another, the sequence of these same values may be anomalous. This means that the trend, or shape of the subsequence may not be normal. We thus define a subsequence anomaly as a rare subsequence of a given length L. An example of such kind of anomaly can be an arrhythmia, or a supraventricular contraction in the electrocardiogram, or an unusual daily electrical consumption. One way to formally define and search for anomalous subsequences would be to use the discord definition. The discord is a subsequence of length L that has the highest distance to its nearest neighbor. In this example, the discord is the red dot, which is defined above, has the biggest distance dj to its nearest neighbor than every other point. The advantage of this definition is its mathematical simplicity. Nevertheless, it has drawbacks. In the specific case of a very large data series in which multiple similar anomalies are present, the discord definition will fail to identify these anomalies. This situation occurs, for example, in an electrocardiogram with several supraventricular contractions. In this first example, the discord, which corresponds to the highest point in the green data series, refers to a normal heartbeat, and is therefore a false positive. The second example illustrates the same situation in another electrocardiogram with several similar premature heartbeats, which are anomalous. To fix this issue and detect what we call collective anomalies, the M-discord has been defined as the subsequence with the highest distance to its M nearest neighbor. As an example, the red dots group is detectable using the third discord definition. We can illustrate M-discord by using the local outlier factor, which is based on similar definitions. We have here a 10,000 points snippet of an electrocardiogram with several arrhythmias in it. As we can see, looking at a neighborhood of 20 to 80 is enough to detect similar anomalies. However, the parameter M is difficult to set. For instance, when the data series is large, like in this case, where we use a 100,000 points snippet of the same electrocardiogram, the 62 similar anomalies are not correctly identified even when we use a neighborhood size between 20 to 80. To address these issues, we propose a general definition and data structure called the normal model. We define the normal model as a subsequence of length LNM that represents the best the normality of the data series subsequences of length L. In this illustration, the normal model can be seen as a set of subsequences of length L, represented as the dotted circle. We consider anomalous the subsequences that have a large distance to this normal model. We describe next how to define the distance d to the normal model. Our method operates as follows. For a given data series T, we compute the normal model Nm. We then compute the distance of every subsequence of T to that normal model. The subsequences with the highest distance to that normal model are then considered abnormal. The goal is now to provide a way to extract this normal model. To compute the normal model, we execute three steps, which we now briefly describe. The first step consists of selecting a set of subsequences from T. We either do it by random sampling, or by extracting a set of motifs of T. We call these two variants norm sample and norm Sj, respectively. The second step consists of clustering the previously selected subsequences using hierarchical clustering and minimum description length to select automatically the number of clusters. We finally score each cluster, using the notions of centrality, frequency and time distribution. We thus compute the normal model as the centroid of the highest scored cluster. We now compare our method to the current state-of-the-art methods for subsequence anomaly detection in data series. We also included two methods, local outlier factor, and isolation forest, that are not specific to data series, but perform well in unsupervised outlier detection for general multi-dimensional data. We run our experimental analysis on several datasets, both real and synthetic. The real datasets originate from different domains, including medicine and engineering. Here are the accuracy histograms of every aforementioned methods and our proposed approaches grouped by categories. We compare the precision at k, which is the number of correctly identified anomalies in the top k positions returned by each method. We notice that our approach is more accurate than the current state-of-the-art methods. This can be confirmed by running a Wilcoxon-signed rank test. This test points out that our approach is statistically significantly better than the other approaches. Regarding execution time, both variants of our approach perform very well. The variant using random subsequence extraction being up to 1 order of magnitude faster than the competing approaches. To conclude, we address the problem of detecting anomalous subsequences within a long data series, and proposed norm approach that uses a data structure called the normal model, which represents the normality of a data series. We provide a large experimental analysis and show that our method outperforms both in execution time and accuracy the current state-of-the-art methods for subsequence anomaly detection in large data series. Thank you very much for your attention.